it further with this course. Just a couple of things to announce. First of all, I removed one exercise, the COVID-19. So you have only one exercise per week. For the one who submitted, I will grade it and take it into account. Hopefully, luckily, only one had done it. This seems to be quite difficult for us at this point. But otherwise, I will check the last ones also. But I think we can do.
I have a question about the deadlines.
Yes.
The first pandas exercise for week 3 had a deadline at 8 AM yes on Sunday instead of midnight.
It's just a mistake from me. It doesn't matter, and those exercises are not strict, so it doesn't matter if it's late. The only deadline is October 31st. That is what really counts, but just that you can't do all the exercises in one day or 1 week, so that's why I have divided those. Progress in more progressively, a bit more difficult ones for every week, so you have something to do for all the weeks. But it's not that serious if you miss some of the deadlines during this period. Another thing I also wrote in Teams, it was yesterday evening. One of you students wrote to me yesterday that those Jupyter notebooks don't run on your laptops. I'm myself using quite fast desktop computers with a lot of memory, so it's not a problem for me. But I can understand that it is a problem with a laptop with, for example, 8 GB or less memory. So I talked about it before, that there is the Center for Scientific Computing in Finland, which gives the possibility for academic users to use these very powerful computers. And luckily, these Jupyter notebooks can be found using this Hakalogin CSC site. At least all the notebooks that it's very easy to use if you can load the Jupyter notebook file, which then downloads the data. So it works quite nicely. No, I didn't have time to search anything for you, but it works. Anyway, it works. Okay, I can download the dataset here. So let's take this one. you should be able to, if you download these to your computer, then you can upload the computer file here. Those should be somewhere in my computer. I can't find them. Okay, I'm not using time for that today because I think you can manage with that one. So you can just upload the files from your local computer here. So, and they seem to be running quite nicely. I checked it with another computer. Now, I didn't have time this morning to prepare everything for this my lecture computer. But that solves the problem with the resources. If you still have problems, at least me as a teacher could log in there with no problem. If you can't do it, then please inform me. But it seems to be working. There are quite a lot of stuff here which can be run via browser. So that was the information part. About the exercises, you have many of you have returned these, so that's really nice. This week we have only essays because I removed one of the exercises here, so you can get away a little easier. This Titanic Dataset may be quite difficult, but there are examples in Kaggle, so you can take some advice there. Kaggle.com. You can find the Titanic Dataset there, but you can find by yourselves. And this classification is just the chapter 3 of the book, and the related data to the notebook file. You just tweak some of the parameters. If you can get the better accuracy on the test set. So it shouldn't be too difficult. Some of you complain that this course is getting too difficult, but so I tried to make it a little easy. And as I have said before, I haven't got time to check every detail of these exercises. So there can be things that cannot be solved properly. It's always possible, but on the other hand, you are now, maybe this is about the last course you have before you go to the company projects and thesis. So I guess it should be a bit challenging. You have only some general courses about working life skills and such in January, if I remember correctly. So this is the normal case when you go to the work life, that not everything is always given, and you must sort some things out by yourselves. But I try to help as much as I can with all these things. They are not too easy. They're both mathematically and this Python codes get quite complicated quite soon. And I'm not going to even try to explain every detail of this material. I just pick up some key points. Okay, now where we were studying this California housing data, and we had these different error measures. Okay, here it's explained how to get the data that we did. Then the pandas data frame shows easily these parameters. Most of them are numerical, so that's quite easy. Float 64. This ocean proximity is a string, and that's not very easy to process. So in the below text, it is explained in detail how to change it into numerical values, which is easier to process. The histograms give the general look of how the data is distributed, but I'm not going to there today. So here is explained how to create a test set, so that you first train your model and then you apply it to the test set, which should represent the data as accurately as possible. So just pick randomly some part of the original data set which you set aside, and you only use it when you have the ready-made model, like the and as told you last week, the simplest model could be a straight line, but it can be very much more complicated also depending on the problem. Okay, at least we can understand this command, what it does. It splits the data set into train and test sets. So the training set contains about 60,000 data points, and the test set about 4,000. Okay, this program generates every time a different test set, which is not good. So you should pick up a fixed set of data points that you use for test. And here is explained how it's done in Python. It's also possible to split the datasets in multiple subsets in various ways. This one concept I maybe should clarify a bit. This is stratified sampling. This means that the dataset should reflect the number of things in this data set. For example, if you have females and males and you don't have 50% and 50%, then you should have more females in your data set than males. So this is called stratified sampling. The sample should also always present very accurately the whole data, whole population, and for that reason, you should use this stratified sampling. In this California housing example, the number of housings in different categories is different, which we will see later. So for that reason, the stratification must be done. Okay, here is the histogram of income categories, so they are not evenly distributed. So there are these two categories contain more people than this one. So here is just a comparison with the random stratified sampling. In this error column, we see that using the stratified sampling, the error between the overall and stratified is smaller than if we just take random samples. Then it's usually a good idea to get some kind of visual interaction or about the data you are going to analyze. We tried to run we have had in mind that we could use our school's virtual servers to analyze the data, but then there are no graphical user interface whatsoever in those virtual servers, so it was not very good option, because it's quite essential that you can see all the plots. So there are of course many things, many different kinds of plots. Here are they are just filled circles, and here is the alpha channel added, or transparency, that the more people there are, the darker is the circle. There easily can be seen that California, two big cities, San Francisco and Los Angeles. And then you can also add color. Human brain is very good at distincting different colors. So here it's very easy to see those red areas that in this case have large housing prices, expensive, and blue is cheap. And larger circles indicate areas with large population. One of the most important concepts in any statistics is, of course, the correlation coefficient. It can have values between -1 and 1. If the value is 1, then there is full positive correlation. So it's a straight line where all the observations are exactly in the line. And if it's 0, then there's no correlation. And if it's negative, then there is negative correlation. Of course, if you correlate median house value with median house value, you get the value of 1 because of course there is one-to-one relationship. And if you correlate median house value with median income, it's also easy to understand that richer people can have more expensive houses, so this is quite large correlation. But then there is, for example, negative correlation between population and median house value. And usually these correlations are presented visually, where you have these two variables that you are correlating, one in x-axis and one in y-axis. And here you, for example, you see a positive correlation. It doesn't matter, the slope doesn't matter, as you see here. All these lines have correlation of 1. And all these correlations have -1. And here where it's horizontal, there is no correlation. So these two variables don't depend on each other. Usually we see something like this. If there is some trend, then there is some correlation which is less than 1. But if it's just like shotgun target, then there is no correlation. So it should be noted that this correlation coefficient only measures linear correlations. For example, in this bottom row, you see two variables which are clearly correlated in some more complicated way. But the correlation coefficient is still 0. And this pandas can be used quite easily to plot different parameters. So for example, in this image picture, you can see that there is some correlation between, okay, I guess this is median income and median house value, as I already said. Then median income and median house value, again, another way around, this is the same. But for example, here you, at least for my eye, I can't see any clear linear correlation between the variables. So the correlation coefficients are quite close to 0. This was seen here. So only this one is large. The rest of all the rest seem to be quite close to 0. And there seems to be a price gap here. So the prices end at 500,000. And there also seem to be some very weak horizontal lines. And these horizontal correlations should maybe be removed, or something must be done, because they are more or less quirks or outliers in the data. Okay, then there are some words about the data cleaning. So you should always drop all the missing value. You should do something about the missing values. You must decide what to do. And there can be not the numbers, for example, for somehow there is bad data. Usually, if you are dealing with the data that comes from some, for example, IoT device, then there easily can be missing data. So data cleaning should always be done. So you can, for example, if it seems that there is that some parameter doesn't correlate with anything, you can get rid of the whole attribute. And then if there are missing values and you can't drop the whole attribute, then you can replace the missing value with 0, the mean value of the whole data, or the median value of the whole data. And there are these Python functions you can use, drop or fill. I'm not going through this API paths now. Then just some words about this text attributes. So I already said about this also proximity. You can change those in, for example, in replace by numbers. So 0 corresponds to this less than 1 hour from ocean. Clearly, these first values here are zeros in this array. Then near ocean is number 4, and so on. Inland is number 1. So now it's much easier to handle with these mathematical routines. So there might be a problem related to this, because these algorithms will assume that 2 nearby values are more similar than 2 distant values. But that's not maybe true in this case, because also proximity 0 and 4 are closer to each other. Less than 1 hour or near ocean are closer to each other than inland, which is number 1. Then it is possible to use so-called one-hot encoding, that this array is replaced by a matrix. Now you see the number 1 is here, then there is these other possibilities are zeros. And this is the same array as here, just widened into a matrix form. This is so-called sparse matrix. A few words about the future scaling. When you have different data that have very large variation, then you could normalize the data, for example, with min-max scaling, where the values are scaled and shifted so that they range from 0 to 1. Another way is the standardization, which first subtracts the mean value of the data and then divides by the standard deviation. I skip the pipelines here. Let's go this select and train a model part. So here in this example, we first train the linear regression model. And without going into details, we get the labels and predictions. And then measure the goodness, this root mean square error. And you get quite a large value, 68,000 compared to these numbers. It's percentages. Percentage-wise, it's very large. So we have to zoom our parameter. So this linear regression is not the optimal model. Then in this exercise, they train a decision tree regressor. What is a decision tree? I can show you. It's quite simple. It's just you have always two possibilities, true and false, and then you decide according to certain rules and which way you go. There was this example somewhere. Wait. Just this one. Wait. That one. No, it's the same. In principle, it's just that, for example, if you are buying a computer, then you have some steps where you decide that it should it be more than 8 gigabytes of memory. If the computer has less than that, then the decision is no. And for example, if it should have a i7 11th generation i5 Intel processor, then yes or no. If it has, then you go further to the next step. Otherwise, you skip it, and so on. So it's not more complicated than that. It can be used also in this linear model. And in this case, the error seems to be 0, which can't be realistic. And this is an example of overfitting. As you may remember, there was this image where you fit high-level polynomial to some data points. So it goes through every point Of course, then the root mean square error is 0, but it doesn't, it's nonsense. And in this case, this linear decision tree model is overfitting our dataset. Then this can be avoided using this cross-validation. Okay, let's see an image of that. I prepared yesterday that I show you some images, but now. Okay, in principle, you have several decision trees from the same data set. And what is this Wikipedia page? Oh, I can't find the image now, which I found yesterday. So this cross-validation divides the dataset in several subsets, and then each of these subsets are evaluated as decision tree, and it gives some final result. For example, if you run this cross-validation 10 times, you maybe have the same results for the decision tree 6 times and another result for 4 times. Then the final result is that one which gives more the 6 times the same result. And in this case, the result, of course, is not that good anymore. Here is the RMSC now, the error score. Wait, no, this one. This is okay. This is the error score. It's much better than before, but and it seems that this cross-validation gives better fit to the original data. This grid search you should do in the exercise. In principle, you define certain number of parameters that are varied, and then you, for example, in this case, max features and n estimators, which are not explained in this chapter. I don't remember what they are, but anyway, you vary these parameters and then select which gives the best result. And the best result is the lower this RMSE score is. And the lowest value, for example, is this. And when you have the model, then you should evaluate it. And then launch and monitor. But let's now go to chapter 3. There are some points there. Here is the Eminence, for example, for the first thing. Here is the Eminence Data Set, which you need some of the exercises. And of course, it can be found in here. So the idea here is you have a very large set of numbers. Was it 60,000 or something like this in this Eminence database? 70,000. And this classification algorithm given in this chapter will explain in detail how to classify different numbers. So is it, for example, is it number 4 or not? So for example, this image, one image in this Eminence dataset looks like number 5, and its label tells us that it really is number 5. So the task is to classify the numbers, first the number 5 and then all the others. So they are handwritten. So for this case, the training set and test sets are already prepared. And here is explained how to pick a binary classifier. So it's either, so the one image is either 5 or not 5. So something about these performance measures. The simplest way is the accuracy. So how many correct 5s there are with respect to whole data set. For example, in this case, it finds the correct number 5s in 95% of the cases. So it seems that this accuracy is very good. But then if you think it another way around, 90% of those numbers are not 5. So if you guess any number, that is it 5 or not, if you guess it's not 5, you get the right answer in 90% of the cases. Because only 10% of the numbers on the images represent number 5. So in this case, it seems that this accuracy is not the best possible measure of goodness. For this purpose, this is not only related to machine learning. It's I have come across this confusion matrix in medicine also, where you classify, for example, illnesses. And what this confusion matrix does is that you have in this here you have predicted images, and here are actual images. So true positive identifications are those when this algorithm gives you the answer at this number is 5. False positive is that the algorithm gives you the answer at that this image here is number 5, which clearly it isn't. It's number 6. False positive. Then here you have false negative. So the algorithm tells you that these two are not number 5, but actually they are. And here you have two negatives. So all these numbers are not 5, so it's correctly classifying these, not 5s. In an ideal case, you would have all the 5s here in lower right corner and all the others in there. But in practice, there's usually some classification errors or misclassifications. And then for these numbers, we can calculate some further parameters, precision and recall, which are given here. Precision is true positives divided by true positives plus false positives. And another parameter is recall or sensitivity, or true positive rate, which is true positives divided by true positives plus false negatives. We get to the examples a bit later. And then you have a so-called F-score. In ideal case, this is 1 or 100. It combines these two, precision and recall, in one formula. So in ideal case, if both precision and recall are 1, then this becomes 1 divided by 2 multiplied by 2, which equals 1. But unfortunately, precision and recall can never be both 1. So when one gets better, the other gets worse. Here is an example. For example, it was in the news maybe just a few weeks ago that Apple tried to make an algorithm to detect child porn from camera images. So they used some kind of classifier like this to classify those images. For example, if you train a classifier to detect videos that are safe for kids, you would probably prefer a classifier that rejects many good videos, which means low recall, but keeps on the safe ones, which have high precision. Rather than a classifier that has much higher recall, but lets a few really bad videos show up in your product. On the other hand, suppose you train a classifier to detect shoplifters. It is probably fine in your classifier if your classifier has only 30% precision, and as long as it has 99% recall. So then the guards will get a few false alerts, but almost all shoplifters will get caught. So I think that's quite nice example about this precision and recall what they mean. So I said both can't be high at the same time, which is precision recall trade-off. So here's an example again about these are the same images than before. Now we have a decision function and we have some threshold which assigns these instances to the positive class, or otherwise it will classify them negative class. So for example, here the positive predictions give 4 5s and 1 6. So there are 4 true positives and 1 false positive. And here you have 2 so here are 2 false positives and these other are true negatives, which are not 5. Four true positives, 1 false positive, and then the precision is 80%. So you have 4 out of 5 correct. But you have actual number of 5s is 6. And this classifier only detects 4. So the recall is 67%, 4 out of 6. If you raise the threshold or move this arrow to the right, so now you get all the positive 5s. And this 6 becomes true negative. So now it's classified correctly, it's not 5. But then 1 true positive because false negative, this 5 here gets classified wrongly. So precision is now 100%. These are all correctly identified as 5. But the recall is down to 50%. Only half of the total number of 5s is correctly classified. So we can't set this threshold by ourselves, but that this scikit-learn will set the threshold directly. So usually this precision recall, as said, they work as oppositely to each other. So when one of those goes down, the other one goes up. For example, if you set the threshold for some value variable here, then the precision is about 0.9 and this recall is just about 0.4 and so on. It's always a compromise between these. And you can also plot this in precision recall diagram or plot. In principle, when you analyze the results, you should have this going at as high as possible in this upper limit, as long as it could. But then the classification is better the higher this blue line or this blue curve goes. Another way to give the goodness of a classification is this ROC or receiver operating characteristic curve, which is again calculated from these previous values. We have the recall here and false positive rate, which is defined. Somewhere was the formula. I don't remember by heart all these mathematical. Okay, the false positive rate is the ratio of negative instances that are incorrectly classified as positive. It is equal to -1 minus the true negative rate. And this curve also should go as high here towards this top left corner as possible. This would be, this straight line here is purely random classifier. And a good classifier stays as far away from that line as possible. There are quite a lot of different definitions, and new things here, but hopefully at least some of these concepts will get clearer when you do the exercises. I forgot to. There was the definitions, mathematical formulas for those somewhere. Oh, yeah, they were. Okay, let's just take this final classification here. When you now classify all the numbers from 0 to 9, you get this kind of confusion matrix. Here are the numbers 0, 1, 2, 3, so on until 9. And also here. Now in ideal case, only this diagonal would contain values, and all these non-diagonal elements, they are all misclassified. Should be 0. This can be also shown as an image where the ray level value tells how large number here is in the matrix. So most of the images of the main diagonal are classified pretty well. So when divided by the number of each how many numbers there are in each category, so how many zeros, how many ones, and so on, you get this kind of image. And now it seems that this number 8 has something strange. So the rows represent the actual classes and columns represent predicted classes. So when this is bright, so the number in this matrix, numbers in this column are large, it means that there are quite a lot of misclassifications for this number. But there is no such thing in this row of 8s. So that tells us that the actual 8s in general get properly classified as 8s. But other 8s get classified as 8s, but also other numbers get classified as 8s, which is this bright column here. Also, you see that the numbers 5 and 3 are brighter than others. So they get more often confused with others than the other numbers. But I'm not going any further in this classification theory now. We continue here next week. This is quite tough theory to lecture for me, at least. So I guess I don't have any further for today. Again, if you have any questions, you can ask by email or Teams. I try to solve the practical problems. And if you have problems with the CSCs to be the notebook, please inform. Okay, have a nice day. See you.